Notice V naught by Vi, the complex number is 1 by 1 plus j omega RC. Question is, what happens to phase? If omega tends to 0, what happens to phase? So now again, with respect to omega, we want to plot phi. Okay, let's forget this nuisance over here. We want to know what happens with respect to phase. So if omega tends to 0, what is the phase here? Phase is also, angle of V naught by Vi. That was also simple, right? The top angle is 0, bottom angle is tan inverse omega RC. If omega is 0, this is tan inverse 0, phase is 0. If omega tends to infinity, what happens to phase? This I am calling it as phi. Simple, bro. Tan inverse of infinity, what is that? Notice it's 0 minus pi by 2, so this is minus 90 degrees. So you start at 0 value, you kind of go to minus 90 degrees as omega tends to infinity. So quick question. So do you know the phase at cutoff frequency? If omega is 1 over RC, what is the phase there? That is, here we have omega C. What should be this value? You could easily see that 1 over RC phase equals, again slightly be careful, it's minus pi by 4. Notice when omega equals 1 by RC, this is tan inverse of 1. So minus tan inverse of 1, that is minus pi by 4. So not just the magnitude, we also know what happens to the phase change. There is also phase distortion. Again, we can say, what it says is low frequencies, no distortion. Let's interpret this graph. So again, you plot something like this, we cannot make sense out of this. So we have 0, minus 90, and then we have minus 45 degrees. Okay, this is omega C. This is going to be 1 over RC. If you are given a LR circuit, it's going to be 1 over tau. So that is omega C is going to be R over L. Okay, we'll come to that, but right now this is 1 over RC. Low frequencies, no phase distortion. You want to allow low frequencies, you want to pass low frequencies, no phase distortion or lesser phase distortion. That's a better word. Low frequency, lesser phase distortion. Any change in, this should ideally be the same phase, but it's not. You put in a signal, you want the signal, the same signal. You send in one heartbeat, you want the same heartbeat here. You don't want the, a next heartbeat. The delay shouldn't be so much. Phase is notice time delay, right? So that's distortion. Low frequencies, lesser phase distortion. High frequencies, most phase distortion, and maximum distortion is fortunately in this case, just 90 degrees. Frequency minus 90 degree phase distortion. Okay, see, the whole class actually we started with phasors, but once we went to phasor domain, our hero was the impedance. And the moment you have the impedance, notice V0 over Vi again is ratio of impedances because of the voltage division rule. With the impedance, you can start analyzing low pass filter. If you put an R and L, it will be a high pass filter. If you reverse this, if you put C here, you put R here, again that will be a high pass filter. Okay, just impedances, you could go check all those details. Okay, so what is this circuit? How does this behave with respect to frequency? Again, voltage division of impedances. Redo whatever we did, so let's not redo it. Okay, voltage division using impedances. What happens to omega tends to 0? What happens to omega tends to infinity? Then LPF or HPF, LPF or HPF. Okay, and then find out when this 1 over root 2, this magnitude is 1 over root 2. Okay, this corresponds to cutoff frequency. And you don't have, you can actually close your eyes and guess here. What do you think is the cutoff frequency here? If you do all that calculation, omega C should be 1 over tau, that is R over L. And this will behave like, what happens at very low frequency. You could do the math. What happens at DC for an inductor? Inductor shorts at DC, right? So no voltage drop across the inductor. Okay, this will be HPF. You can actually say that without even solving the problem. And omega is C is going to be 1 over tau R over L. Okay, for first order circuits. In fact, right now we are in a position to try this again. Just, the standard steps we did for RC circuit. If it replace R and C, you are going to get a different response. This is a different circuit response will be very different. We studied this. This response will be very different. This was LPF. This will be HPF. Beware. Okay, but the cutoff frequency will be the same. Still 1 over tau. But whether it's high pass or low pass will change. Z simplified our life. Simplified our life. Okay, there are two mnemonics: cos omega t, sin omega t. With this, all this, you can get all the trigonometric identities. Then you had simple mnemonic. Then you have omega is 1 over tau. So first order circuits, whether it's where the cutoff frequency is. Okay, and high pass, low pass also you could quickly say. Today we did sinusoidal and frequency response. Yeah, we did at least one filter properly. There are only like 4 first order filters. Okay, Bode plot we'll do separately. We will get back what are some applications of first order circuits in biomedical engineering. Actually, a lot, ton. Okay, bioinstrumentation is, most of bioinstrumentation is based on this, whatever we learned right now. And if you know second order circuit, it will also complete the picture.